Hello everyone, my name is Neal and I am a PhD student from the University of Michigan, advised by Professor Baris Kasikci. And in today's talk, I'm going to talk about our system, AGAMOTTO, which we designed to automatically detect bugs in persistent memory storage systems. So at last, Intel has made persistent main memory commercially available. This is a higher capacity main memory technology which resides in the memory bus alongside traditional DRAM, providing a large pool of memory at only 2 to 3 times higher latency. This new technology has two main potential uses. First of all, it can be used to simply increase the size of volatile main memory, or it can be used as durable storage due to the non-volatile nature of the underlying medium. Furthermore, as persistent memory is main memory, it can be mapped directly into a process's address space, allowing an application to directly manage persistent data structures without file system overhead. Today, I'll be talking about persistent memory as it is used as a persistent storage device through direct access. So using persistent memory as durable storage requires using special persistence mechanisms, or durability mechanisms, to ensure updates to persistent memory become durable. Let me demonstrate. Let's say we want to make x a persistent value. First, we issue a store to x. This creates an update that becomes cached in the CPU cache. However, we don't want to leave this update in the CPU cache, since it is volatile, and a crash would cause the update to be lost. Therefore, we need to issue a flush instruction, which tells the CPU to write the update back to the backing storage device, which in this case is persistent memory. However, this flush instruction can be delayed by the CPU, as it is weakly ordered with respect to other instructions. Therefore, we also need to issue a memory fence, which will force this flush instruction to finish, writing the update all the way back to persistent memory. Now so far, writing updates to persistent memory hasn't seemed that difficult. Add a flush and a fence to a store? Seems like a piece of cake. However, we encounter some issues as we begin to write more complex applications. We can continue to write flushes and fences after every store, which makes it easy to reason about the ordering of updates in the application, but it becomes slow as you essentially have no memory parallelism in the system anymore. So instead, application developers write more clever code, trying to consolidate expensive memory fences and group flushes together. This can give better performance, but it becomes harder to reason about the ordering of our updates, and this can quickly and easily lead to persistency bugs. These persistency bugs can have dire consequences, such as permanent data loss. For example, if either the flush or the memory fence instruction are missing, the update to X can be lost on a power failure, resulting in possible data corruption. These bugs can also be difficult to find due to non-deterministic factors. For example, if the flush and the fence are both missing, the update to X can still be persisted due to a cache line eviction. Furthermore, the cache state and the state of persistent memory are opaque to developers, and so traditional debugging tools like GDB cannot be used to check whether or not an update has been properly persisted or if it only resides in the volatile CPU cache. We therefore need persistent memory-specific debugging tools to help us reason about these bugs if we have any hope of finding them. Of course, we are not the first group to think of this problem, and others have built persistent memory-specific tools in the past. However, they suffer from a range of shortcomings, from requiring extensive, manually created test suites to avoid low testing coverage, to requiring source code modifications, or being too specific to a particular persistent memory system or API. Overall, we find that prior work requires too much effort to use and has too little testing coverage. We would much prefer a tool which didn't require us to modify applications and which had fewer false negatives, or missing bugs due to a lack of testing coverage. This examination of prior work led to our work. We first performed a study of persistent memory bugs to determine what real bugs look like in practice. We examined a number of bugs across different applications and found two predominant patterns of persistent memory bugs. Importantly, we discovered that these patterns are independent of program semantics, and they can be detected automatically with no source code changes. We then used these patterns to inform the design of our tool, AGAMOTTO. AGAMOTTO is a symbolic execution tool, and we leverage symbolic execution to eliminate the need for large, curated testing suites by testing many program paths symbolically. We build AGAMOTTO on CLI and augment it with 3 persistent memory components, which allow AGAMOTTO to support symbolically executing persistent memory applications and rapidly detect any persistent memory bugs they may have. Finally, we demonstrate the usefulness of AGAMOTTO. We use AGAMOTTO to find 84 new bugs across a variety of persistent memory applications. To compare, some related work, PM-Test and XF Detector, find 3 and 4 new bugs, respectively. We were also able to confirm many of these bugs with developers, validating our results and helping developers produce more reliable systems. Finally, we perform a novel study of performance bugs and show that by fixing performance bugs, we can improve performance by up to 47%. This demonstrates the importance of finding both persistent memory bugs which affect correctness and persistent memory issues which impact the performance of programs. First, I'll discuss the results of our bug study. In this survey, we surveyed 63 previously documented bugs. Most of these bugs were from PMDK's issues tracker, as that is the most mature open-source persistent memory system available, but we also analyzed some from prior work. As I previewed earlier, we discovered two predominant patterns, which we used to create application-independent bug detectors in AGAMOTTO. The first pattern we codify is the missing flush and fence pattern. Here's an example of what this bug looks like. In this example, a modification is made to OID, which points to persistent memory, but it is not made properly durable, as there are no associated flushes and fences. This pattern is therefore defined as a persistent memory update not being made properly and explicitly durable. Furthermore, we find this pattern across a variety of applications, and it is not dependent on any specific API. We also find that this pattern accounts for the majority of bugs in our survey, accounting for almost 80% of our surveyed bugs. We do note that there are ways of writing persistent memory applications which would violate this pattern, but we don't discover any in our testing. The second pattern we codify is the redundant flush and fence pattern. Here we look at a similar example. In this example, OID is properly made durable, but then redundant durability mechanisms are issued after the update has already been made durable. These redundant mechanisms are therefore unnecessary and serve no purpose. Furthermore, these redundant instructions are a potential performance issue regardless of application semantics, and can occur in a variety of applications. We note that this pattern is the second largest class of bugs in our survey, comprising 11% of the bugs we surveyed. To summarize, we find that 90% of the bugs have one or two application-independent patterns of persistent memory bugs. This allows us to create automatic detection mechanisms which don't have to be tailored to specific applications. However, there are still some application-specific bugs in our survey, about 10%, that we don't want to ignore. However, rather than have developers modify their source code, we believe that they should instead supply their own bug patterns. This pattern-based bug methodology allows us to avoid having to require any source modifications. This makes it much easier to adopt a new testing tool and much easier to find bugs in a variety of systems. Now I want to discuss how we built AGAMOTTO to find new persistent memory bugs using the bug patterns we found during our survey of real persistent memory bugs. First, however, I need to give some background about how general symbolic execution works before I get into how we extend it to support persistent memory bug finding. So in symbolic execution, we're essentially executing a program. We start out by picking a symbolic state, which represents the state of the program execution at a particular program counter, and includes the values of local variables in memory. We then execute the current instruction and increment the program counter. We then update the state based on the result of this instruction. In this case, we update the value of doRead to be a symbol, which represents any value rather than a concrete value like 1 or 0. This is the main difference of symbolic execution over real program execution, and we can see that how the program runs when doRead is any value rather than a specific value for a unit test case. Now we can see how symbolic execution gets such great testing coverage. We'll execute the next instruction. So again, we select our state. We then execute the conditional branch. We then update the state, and this causes the state to fork, meaning that the state splits on the conditional statement so that the symbolic values can be consistent with the control flow of the program. In the if block, the statement is only reachable if doRead is not equal to 0, otherwise the statement would have evaluated a false. So now the state contains the symbol where the symbol has been constrained to be any value not equal to 0. Likewise, the only value of doRead that would allow the program to reach the else block is if the value of doRead was equal to 0. Therefore, in this state, the value of doRead is simply 0. This thorough path exploration is why we built AGAMOTTO as a symbolic execution tool. We can use symbolic values to easily explore many program paths, unlike our related work which relies on concrete unit test cases to explore one path at a time. This easily gives us high code coverage when finding persistent memory bugs. Alright, now that we have the symbolic execution background out of the way, let's talk about how we implement AGAMOTTO. So the first issue we need to address is how we allocate persistent memory, for example through mmap, and how operations are performed on persistent memory, for example through the store to persistent memory in pbuff. To do this, we augment CLI with a persistent memory model. This model adds functionality to CLI by extending the symbolic memory model to include persistent memory state. We also allow applications under test in AGAMOTTO to allocate persistent memory through the mmap interface. High-level APIs ultimately make low-level calls to mmap, and so we can still test systems like PMDK this way. The way that persistent memory state works is as a state machine. Every region of persistent memory has one of three associated states. It is either clean, dirty, or flushed. The persistent memory model then functions as a state machine using the different persistency mechanisms as state transitions. For example, stores will make any state dirty, which indicates that it needs to be flushed. A flush then moves persistent memory to being flushed, and then a fence on a flush state will finally make it clean again. This reflects the example discussed at the beginning of the talk, where we needed to flush and fence an update in order for it to become clean again, or made durable. Now that we've modeled persistent memory, the next thing we need to do is actually find bugs in persistent memory applications. In this updated example, the highlighted state is about to terminate since it's about to execute this exit call. However, there's a persistent memory bug, as pbuff of x is flushed but not clean. So we detect this bug by augmenting AGAMOTTO, or augmenting CLI, with a set of persistent memory bug oracles, which run after updating the state after every instruction. So we implement our application-independent bug finders as bug signals on our state transition diagram of persistent memory. For example, to detect missing flush and fence bugs, we look for an exit condition off of dirty or flush states. This is a bug because the states had not been properly made durable. Likewise, for the redundant flush and fence pattern, we look for when a flush or a fence occurs from a clean state or when a flush occurs from an already flush state. As I hinted at earlier, there are still application-specific bugs that we would like to detect. To enable this, we allow developers to easily encode custom signals and states into this state machine model of persistent memory. I'll give an example of application-specific bug ordering. So let's say that we have two data structures and A must be made durable before B. So modifying A works as before. A becomes either clean, dirty, or flushed. However, we have new state transition signals when B is modified while A is not clean. In this case, where A is dirty or A is flushed, this indicates an ordering violation because A has not been properly made durable before B. However, if B is modified when A is clean, everything functions as normal and no bug is detected. We ultimately use this API provided by AGAMOTTO to accurately detect all of the user space persistency bugs reported by PM-Test and XF Detector by building two such custom bug oracles. So the persistent memory model and the persistent memory bug oracles require everything that AGAMOTTO needs to find persistent memory bugs. However, we also want to build a persistent memory state selection method to mitigate one major issue of symbolic execution: state space explosion. So what is this problem? Well, in our examples, we've been using fairly small programs. However, for real programs, there are many repeated conditional branches, which can continually fork and fork and fork the state. Furthermore, loops exacerbate this issue, as the process of forking can be repeated many times, leading to this exponential explosion of states. However, we're only interested in exploring states which have persistent memory bugs, because we only want to look at these persistent memory bugs. So we ask ourselves, can we accelerate bug finding by driving exploration towards states which are likely to contain persistency bugs? And we are. Our insight is to drive symbolic execution towards states with more persistent memory modifying instructions, as these states have a greater chance of having persistent memory bugs, as persistent memory bugs originate from bad modifications to persistent memory. So what we did was we created a method for identifying states which are more likely to modify persistent memory. The first thing we do is we find all instructions which may modify persistent memory using a static analysis, which tells us which instructions may modify memory, which may point to a persistent memory allocation site. To be application independent, we consider mmap sites to be these persistent memory allocation sites. We then assign all of these instructions a unit weight of 1, and then we backpropagate these weights to form a per instruction priority, which represents the number of reachable persistent memory modifying instructions from that point in the program. For example, the instructions in the else block have a positive priority, and the instructions in the if block have a priority of 0, since there are no reachable NVM modifying instructions from this point. Then, during state selection, AGAMOTTO selects the state with the highest priority. And it turns out in practice, even persistent memory intense applications, less than 10% of all instructions have a non-zero priority, meaning that we're actually able to select high priority states over low priority states even in real systems. So in summary, to build AGAMOTTO, we augment CLI with three main things. We add a model for allocating and modifying persistent memory, and also for tracking the status of persistent memory in symbolic states. We also add bug oracles, which use persistent memory state transitions to detect our patterns of application-independent bugs. This also supports custom bug patterns so developers can detect application-specific bugs. We also develop a state selection algorithm which drives symbolic execution to prioritize execution of states which are more likely to contain persistent memory bugs. Finally, I want to briefly discuss how we were able to use AGAMOTTO and the results we found from using it. Most importantly, we found bugs. We found 84 new bugs in a total across the 5 systems we test. Of these bugs, 14 bugs are correctness bugs, and 70 are performance bugs. We also note that our closest related work, PM Test and X-Text Detector, were able to find 3 and 4 new bugs respectively. We also evaluate the effectiveness of AGAMOTTO's search strategy. We compare AGAMOTTO's PM-aware strategy to CLI's default search strategy. After an hour of runtime, CLI's search strategy only found 30% of the bugs that we found in total. In contrast, AGAMOTTO's strategy was able to find all bugs in under 40 minutes. Finally, since we found so many performance bugs, we wanted to know whether or not any of them were majorly impactful to the overall performance of the system. So we performed a case study on Recipe, an academic research prototype, which provides a persistent indexing structure. We found that by fixing all of the performance bugs in Recipe, we were able to increase the performance of the structure by between 23 and 47%. This demonstrates that these performance bugs should not be ignored. We were also able to report some of these findings to developers, not only to help validate our bug findings, but also to help them develop more reliable systems. Importantly, we got some very positive responses from these developers. Overall, none of these developers reported any false positives, and so all of our bugs were real bugs. Furthermore, developers noted the benefits of AGAMOTTO and appreciated its thoroughness and ease of use. Notably, we had several comments about the lack of good testing tools, which we were able to address successfully in AGAMOTTO's design. In conclusion, we performed a study of persistent memory bugs and discovered 2 application-independent patterns of bugs. This insight allowed us to build AGAMOTTO, which leverages the power of symbolic execution in combination with application-independent bug patterns to accurately and automatically detect persistent memory bugs. We then use AGAMOTTO to find 84 new bugs in a variety of persistent memory applications. We also demonstrate the performance impact of persistent memory performance issues, showing a throughput increase of up to 47% in our performance case study. AGAMOTTO has gone through the OSDI 2020 artifact evaluation process and has earned all 3 badges. You can find AGAMOTTO's source code and other documentation relating to its usage at the link provided in this slide. Thank you for listening to my talk. Feel free to reach out to me about any questions that you may have on our paper or about using AGAMOTTO. Thank you.